Let's begin with a simple question. If the universe is so vast, so old, and filled with billions of stars and planets, why aren't aliens already here? It sounds like a question from science fiction, but it is really a question about physics. Physics does not negotiate with imagination. It asks what the rules are, what can happen, and what cannot. Tonight, we will explore those rules carefully, honestly, and with curiosity, without exaggeration or hype. To understand why interstellar travel is so difficult, we must first grasp the scale of the universe. Imagine shrinking Earth to the size of a marble. The sun, in this scale, becomes a beach ball 30 meters away. Where is the nearest star? Not the next planet, not Mars, not Jupiter. The nearest star, Proxima Centauri, would be thousands of kilometers away. Even though we say that the nearest star is just over 4 light years away, the human brain cannot intuitively understand what a light year represents. A light year is the distance that light travels in 1 year. Light travels at roughly 300,000 kilometers per second. In 1 second, it can circle Earth 7.5 times, even at that mind-boggling speed. It still takes over 4 years to reach the nearest star. And this is just the beginning of the problem. Nothing that has mass can reach the speed of light. This is not a technological limitation. It is a law of nature. Einstein discovered that as an object with mass moves faster, the energy required to accelerate it grows. The closer it gets to the speed of light, the more energy is required, and eventually the energy needed becomes infinite. To accelerate any object with mass to the speed of light would require infinite energy. It is not simply very large, it is mathematically impossible. Suppose we are generous and assume that a civilization could build a ship capable of traveling at 10% of the speed of light. That is 30,000 kilometers per second, an unimaginable velocity by human standards. Even then, reaching the nearest star would take more than 40 years. Reaching planets 100 light years away would take a millennium. Crossing the galaxy would require hundreds of thousands of years. The scale of the universe imposes an almost insurmountable barrier. The distance between stars is so vast that even civilizations far more advanced than ours would struggle to reach one another. These distances are not just numbers. They reshape the way we think about interstellar travel. They demonstrate that even if aliens exist, they are confined by the same physical laws that govern us. Space is not merely vast, it is empty in a way that compresses imagination into futility. It is a realm so sparsely populated with matter that even traveling at incredible speeds encounters with the environment, dust, radiation, cosmic particles, pose existential risks. The vastness is not only a matter of distance, but of energy, risk, and time. Every journey across the stars becomes a monumental undertaking, a challenge that is less about ambition and more about the fundamental limits imposed by the universe itself. Understanding this begins to explain why, despite the universe's age and size, the cosmos may appear silent. It is not necessarily devoid of life. It may be that the sheer scale of space, coupled with immutable physical laws, creates barriers that even intelligent civilizations cannot realistically overcome. The silence is not proof of emptiness. It is the echo of vast distances, the consequence of physics, and the reminder of the limits that define all possible journeys. Einstein discovered something remarkable about the universe, something that sets an absolute speed limit for everything with mass. The faster an object moves, the more energy it requires to keep accelerating. As it approaches the speed of light, the required energy grows without bound, ultimately becoming infinite. It is not a matter of engineering skill or future technology. It is a law of nature. A spacecraft, no matter how advanced, cannot reach light speeds. That simple rule shapes the possibilities of interstellar travel in ways that are difficult to grasp. Let us imagine a civilization that has solved every engineering problem except this one. Suppose they build a spacecraft capable of traveling at 10% of light speed. That is 30,000 kilometers per second, a velocity far beyond anything humans can currently achieve. Even at this speed, traveling to the nearest star would take more than 40 years, a journey longer than a human lifetime. For stars 100 light years away, the journey stretches over a millennium. Traveling across the galaxy would require hundreds of thousands of years. No matter the ingenuity of a species, distance imposes a harsh limit. The cosmos is simply too vast to cross quickly. Distance is not the only barrier. Energy presents another, perhaps even greater, challenge. Accelerating a spacecraft to such tremendous speeds demands unimaginable energy. To push even a small ship weighing the mass of a large building to 10% of light speed would require a conversion of matter into energy on a scale humanity cannot fathom. And the energy needed to decelerate upon arrival is equally immense. Interstellar travel is not merely a problem of better rockets or fuel. It is a problem of civilization scale energy management. It is a challenge on a scale that may be unachievable, even for species far older and more advanced than ours. Even if these technical hurdles could somehow be overcome, time introduces a psychological and practical barrier. Imagine launching a ship that travels at 20% of light speed toward a planet 200 light years away. From the perspective of Earth, the journey will take 1,000 years. Even if the crew experiences some relativistic time dilation, civilization on the home planet will have changed beyond recognition or disappeared entirely before the ship arrives. Investing in a mission of such duration requires planning over timescales that challenge human comprehension. Humans struggle to commit to projects lasting decades. Sustaining a mission across centuries or millennia presents an almost insurmountable organizational problem. The physical limits of space are compounded by the social and temporal limits of life itself. The hazards of space intensify these challenges. At 10% of light speed, even tiny particles pose enormous dangers. A grain of dust, harmless at everyday speeds, strikes with energy comparable to an explosive. Radiation from cosmic rays in the interstellar medium continually bombards the vessel, requiring shielding that may be impossibly massive. Space is sparse, yet at relativistic velocities, the emptiness becomes lethal. The universe is not hostile in the sense of intent, but it is unforgiving in terms of physics. Travel across it requires mastery of forces that threaten to destroy even the most advanced ships. Even hypothetical solutions such as wormholes or warp drives face similar constraints. General relativity allows mathematical solutions that resemble shortcuts through space-time, but they demand forms of matter and energy that are either theoretical or physically unattainable. Tiny quantum effects may hint at possibilities, but scaling them to a usable form is a different problem entirely. Mathematics permits many abstractions, nature enforces very few. Every shortcut imagined still must obey the laws of physics, and the universe rarely bends to wishful thinking. Now, let us turn to one of the most subtle obstacles in interstellar travel, the limits imposed by time and patience. Imagine a spacecraft moving at 20% of light speed, heading toward a star 200 light years away. From Earth's perspective, the journey will last 1,000 years. Even with relativistic time dilation, where the traveler's clocks run slightly slower than ours, the journey still stretches across lifetimes and centuries. The civilization that launched the mission may rise, change, or even vanish entirely before the spacecraft reaches its destination. The physical journey, then, is not only a challenge of propulsion and energy, it is also a challenge of endurance, continuity, and long-term planning on a scale almost impossible to comprehend. Human beings are naturally impatient. We struggle to commit to projects lasting decades, even a lifetime, and yet interstellar travel demands planning over timescales hundreds or thousands of times longer. The very concept of investment and reward changes when the journey extends far beyond the span of a single generation. Even if an advanced species could build the perfect spacecraft, maintain it flawlessly for centuries, and solve the monumental energy challenges, the problem of time remains. Civilization itself is fluid. Governments, cultures, species, even planets can rise and fall. Planning a mission that outlives nearly all context for which it was intended is a barrier that no amount of technology alone can overcome. Beyond time, there is the problem of space itself. Interstellar space is not a perfect vacuum. Tiny particles, atoms, and radiation fill the void, and at relativistic speeds, these become serious hazards. A speck of dust, harmless at ordinary speeds, strikes with the energy of a large explosion when encountered at a significant fraction of the speed of light. Cosmic rays constantly bombard any vessel traveling through space, potentially degrading materials, electronics, and even biological matter. A ship designed to travel for centuries must be equipped with shielding so massive and resilient that it may approach impracticality. The universe is sparse, yet the sparse medium becomes lethal when combined with high velocity, turning emptiness into danger. Energy, too, becomes a formidable barrier. The faster a spacecraft moves, the more energy it requires to accelerate and then decelerate. Even a relatively small ship, traveling at a tenth or a fifth of light speed, requires energy comparable to converting significant portions of matter into pure energy. This is not a challenge of adding bigger fuel tanks. It is a challenge of generating and managing energy at levels that dwarf entire planetary resources. The laws of physics demand these amounts, and there is no trick or technology that reduces the requirement without violating those laws. Civilization-level energy is not optional, it is mandatory. Some theorists propose exotic solutions such as wormholes or warp drives. In theory, these might shorten distances or bypass conventional travel limitations. But they rely on forms of matter or energy that we have never observed and may never be able to manipulate. They are mathematically permissible, yet physically questionable. Nature permits certain phenomena in equations, but very rarely allows those phenomena to manifest in reality in ways that are useful for interstellar travel. Mathematics can dream, physics decides what can exist. Even if we imagine the most advanced species, with perfect energy management and absolute understanding of physics, the combination of distance, time, energy, and space hazards presents an almost insurmountable challenge. The universe is not hostile, but it is unforgiving. The barriers are not political, cultural, or motivational. They are fundamental. They are written into the structure of reality itself. Even if we imagine that advanced civilizations could overcome energy, distance, and time, there remains a subtle but profound barrier, the nature of the universe itself. Interstellar space is not empty in the way we usually think. It is filled with diffuse particles, cosmic radiation, magnetic fields, and remnants of exploded stars. At normal speeds, these might be harmless. At relativistic speeds, even tiny particles become lethal projectiles. A single atom can impact a spacecraft with energy comparable to that of a small bomb. Over decades or centuries, the cumulative effect of countless microscopic impacts could destroy a vessel. Shielding against these hazards is not a matter of adding layers of metal. The protection required grows with velocity and time, demanding materials and engineering that may be fundamentally impractical. The universe is not actively hostile, yet physics itself becomes a relentless adversary. The more we understand, the clearer it becomes that interstellar travel is not a problem of imagination, creativity, or clever engineering tricks. It is a problem of physical law. Even the fastest, most efficient propulsion methods would require energy and resources on a scale comparable to entire planets or even stars. Civilizations capable of producing and sustaining such power are conceivable in theory, but they face the same constraints as any other. Energy cannot be created from nothing, matter cannot exceed light speed, and time marches forward in ways that cannot be manipulated at will. The universe sets boundaries, and even the most intelligent life forms must operate within them. Hypothetical solutions such as wormholes, warp drives, or other exotic shortcuts are intriguing, but they raise more questions than they answer. General relativity allows mathematical constructs that resemble shortcuts through space-time, yet the matter and energy required to make them stable is exotic, hypothetical, and possibly unobtainable, even if tiny quantum effects produce fleeting negative energy. Scaling these effects to create a traversable passage across light years seems almost certainly beyond the capability of any civilization. Equations may permit possibilities, but nature imposes reality. The universe does not grant magic, it grants constraints. Intelligence cannot bypass physics, it can only work within it. This brings us to one of the most profound mysteries, the Fermi paradox. If the galaxy has billions of stars and countless potentially habitable planets, why do we see no evidence of alien civilizations? The silence of the stars may not indicate emptiness. It may indicate isolation. Even advanced civilizations may be trapped on their own planets by the laws of physics. The distances are vast, the energies required immense, the hazards extreme, and the timescales unimaginably long. Planets may harbor life, even intelligent life, but communication and travel may be fundamentally constrained by the structure of reality. The cosmos may not be empty, it may be compartmentalized, with islands of life separated by oceans of space and time. Even as we confront these limits, we must acknowledge the unknown. Physics is powerful, but incomplete. We do not yet understand everything about quantum gravity, space-time, or the fundamental properties of matter and energy. New discoveries could reveal mechanisms we cannot now imagine. Yet there is a crucial distinction. What we do not know is not the same as what is possible. There is a difference between ignorance and violation of natural law. Just because we cannot predict every phenomenon does not mean interstellar travel becomes trivial. The universe has boundaries, and those boundaries shape the possibilities of life, movement, and civilization. Considering all this, it becomes clear why the silence of the galaxy is not necessarily despairing. It is a reflection of reality itself, of rules that no technology, intelligence, or desire can simply overcome. Life may flourish in countless corners of the universe, but the cosmos enforces its own scale, its own structure, and its own limits. Understanding these constraints does not diminish wonder, it deepens it. It challenges us to recognize the extraordinary subtlety, elegance, and difficulty of operating within a universe that is vast, beautiful, and uncompromising. Now let us reflect on what all of this means. If aliens cannot easily reach Earth, if the distances are too vast, the energy required too immense, the hazards too lethal, and the timescales too long, what does that tell us about our place in the universe? It does not imply that we are special or unique. The laws of physics do not favor Earth, humans, or any particular species. They are impartial, consistent, and unyielding. The silence we observe in the cosmos may not be because life is rare, but because the universe is vast beyond practical connection. Even civilizations far older and more advanced than ours may be confined to their own worlds, unable to traverse the staggering gulfs that separate stars. This realization changes the way we perceive isolation. It is not loneliness born of neglect, fear, or scarcity. It is a structural isolation, a consequence of the physical limits imposed by reality itself. The stars are not silent because they are empty. They are silent because the fabric of space, the speed of light, the hazards of travel, and the finite lifespan of civilizations create natural boundaries. These boundaries are not negotiable. They do not bend for intelligence, desire, or ambition. They are simply the rules that define what is possible. Understanding this reframes the Fermi paradox. The absence of observed aliens is not evidence of absence. It may be evidence of constraint. Life can exist, flourish, and even develop intelligence, yet remain effectively isolated by the universe's own laws. There is a subtle, almost philosophical consequence to this understanding. It shifts our perspective from expectation to responsibility. If interstellar contact is impractical, if rescue, intervention, or expansion across the galaxy is physically limited, then the stage on which life must act is the one it currently occupies. Earth is not a waiting room for the universe. It is the arena in which life unfolds, experiments with complexity occur, and consciousness reflects upon itself. The physical isolation imposed by the universe magnifies the importance of our stewardship here. Understanding that no one else is likely coming, and that traveling to other worlds is constrained by immutable laws, lends gravity to every decision we make. The boundaries of physics are also boundaries of responsibility. Yet, this understanding does not diminish awe. On the contrary, recognizing the constraints of the cosmos deepens wonder. We marvel not despite the difficulty, but because of it. The universe is vast, dangerous, and demanding. Its laws are unforgiving, yet they are consistent, intelligible, and comprehensible. The fact that civilizations may be isolated does not make life trivial. It makes life remarkable. The energy, ingenuity, and cooperation required even to survive on a single planet are extraordinary achievements. The fact that any intelligence has arisen at all, anywhere in the cosmos, is a triumph over the constraints of reality. Perhaps the most profound lesson is this: the universe is not a playground in which all desires are attainable. It is a structure within which intelligence and life must operate, and the constraints themselves define the beauty, challenge, and subtlety of existence. Understanding that interstellar travel may be practically impossible, that even advanced civilizations are limited by distance, energy, and time brings clarity. It transforms the way we see the cosmos. It shifts curiosity from wishful thinking to careful observation, from fantasy to appreciation of reality. In the vast, quiet, and uncompromising universe, we find not despair, but a deeper, more honest awe. We are perhaps the stewards of our corner of space, the inheritors of a rare moment in a vast, silent cosmos. The laws of physics do not bend to desire, but they do reveal truth. By understanding them, we glimpse the extraordinary, subtle, and fragile reality that makes our existence possible and meaningful. The universe is larger than we can imagine, quieter than we hoped, and yet infinitely more fascinating because it operates by rules we can understand if we are patient enough to learn them. Even as we confront the immense physical and temporal barriers of interstellar travel, another layer of subtle limitation emerges: the fragility of civilizations themselves. Every species exists within constraints imposed not only by physics, but by the practical realities of survival and societal continuity. A civilization capable of sustaining a starship for centuries or millennia must maintain knowledge, resources, culture, and political cohesion over durations that surpass human comprehension. On Earth, empires rise and fall in mere centuries. Knowledge can be lost, cultures can collapse, technologies can vanish. Scaling that stability to a timescale long enough for interstellar journeys is not a trivial matter. It may be a barrier as insurmountable as the laws of physics. Even the most intelligent and advanced species may struggle with the simple fact that life, in any practical sense, is ephemeral, while the distances between stars are eternal. Space itself compounds the challenge. The interstellar medium, though sparse, is dangerous when approached at relativistic velocities. Tiny particles, atoms, and cosmic dust strike with enormous force. Radiation permeates the void, damaging materials and biological organisms alike. Maintaining a ship and its occupants for decades or centuries in such an environment is a problem that combines engineering, biology, and energy management in ways that may be fundamentally incompatible. Every kilometer traveled multiplies the risk. Every second spent in motion exposes the travelers to hazards that would seem insignificant at low speed, but become catastrophic under the conditions required for interstellar transit. Space is not hostile in the sense of intent, but it is unforgiving in the strictest sense. The universe does not negotiate with life. Even when theorists propose shortcuts, such as wormholes or warp drives, the challenges are profound. General relativity allows mathematical solutions that resemble bridges through space or time, but the matter and energy required to make these constructs stable is exotic, hypothetical, and may be unattainable. Quantum effects can produce fleeting phenomena, but scaling these to usable levels requires control over nature at a degree that may forever remain beyond reach. Equations can permit possibilities that reality does not. Mathematics can imagine highways through space. Physics ensures that these highways, if they exist at all, are extraordinarily difficult to traverse. The universe is not a playground where intelligence can bend the rules. Intelligence can understand the rules, work within them, and exploit subtle opportunities, but it cannot repeal the fundamental structure of reality. This realization reframes our expectations of alien civilizations. The Fermi paradox, why we have not observed evidence of intelligent life, may be less a question of rarity than a question of practical impossibility. Civilizations may arise on countless worlds, but even if they become technologically advanced, the distances, energies, hazards, and timescales could effectively isolate them. The galaxy may be teeming with life, yet each civilization may be confined to its own planetary neighborhood, unable to reach even its nearest stellar neighbor. Isolation is not a punishment. It is a consequence of immutable laws. The universe allows life to exist, but it imposes limits on how far that life can extend or how directly it can communicate across vast cosmic expanses. Understanding these constraints offers a subtle shift in perspective. We often imagine advanced civilizations as unrestricted explorers capable of traversing light years with ease. In reality, the very fabric of space and time, coupled with the finite endurance of matter and civilization, imposes natural barriers. Life may be abundant, yet contact may be rare. The cosmos may be vibrant in potential, yet silent in actuality. This quiet is not a failure of imagination. It is the consequence of reality itself, a reflection of the subtle and uncompromising rules that govern everything from atoms to galaxies. Recognizing these rules does not diminish wonder. Instead, it amplifies it, revealing a universe that is both infinitely vast and intimately constrained, a place where intelligence and life must operate with extraordinary care, ingenuity, and patience. As we continue to explore the barriers to interstellar travel, it becomes clear that even the most advanced civilizations would face challenges not only of physics but of practical existence. Consider a spacecraft traveling at a significant fraction of the speed of light. The journey to a nearby star system might last decades, while voyages across the galaxy could span hundreds of thousands of years. Civilizations, no matter how intelligent, must contend with the fact that longevity is finite. Societies collapse, knowledge is lost, and technologies degrade. A mission that spans centuries or millennia is not just a question of engineering. It is a question of sustaining a complex, organized, and coherent civilization long enough to see the mission through. Even if a species develops the necessary technology, maintaining continuity over such immense timescales is a challenge that may be just as limiting as the speed of light itself. Time, distance, and energy all combine to create practical impossibilities. To accelerate a spacecraft to a fraction of light speed requires staggering amounts of energy, comparable to converting a substantial portion of matter directly into pure energy. The energy required to slow down at the destination is equally immense. These are not numbers that can be scaled with better fuel or more efficient engines. They are dictated by the fundamental laws of physics. Even civilizations capable of harnessing energy at planetary scales may struggle to provide enough to carry out long-term interstellar travel safely and reliably. Energy is not simply a tool, it is a constraint, a gatekeeper that limits how far and how fast any species can move through the universe. The hazards of space itself impose further constraints. The interstellar medium, while sparse, contains particles, radiation, and magnetic fields that become deadly at relativistic speeds. Even a microscopic particle striking a spacecraft at a significant fraction of the speed of light releases enormous energy, potentially damaging the hull or critical systems. Cosmic rays bombard any vessel moving through space, creating radiation hazards that accumulate over time. Shielding against these dangers requires materials that are incredibly dense, strong, and resistant to long-term degradation. At relativistic velocities, even the vacuum of space becomes an environment of constant, unavoidable danger. The very emptiness of the cosmos is a threat to any travelers attempting to cross it. Hypothetical shortcuts such as wormholes and warp drives offer theoretical hope, yet they remain speculative and likely impossible with our current understanding of physics. Wormholes require exotic matter with negative energy density to remain stable, and there is no evidence that such matter exists in usable quantities. Warp drives, while mathematically conceivable, demand energy levels and space-time manipulations that are far beyond anything that could plausibly be constructed by any civilization. These concepts illuminate the limits of imagination when faced with the uncompromising laws of nature. Mathematics can suggest paths through the universe, but reality constrains which paths can be traversed. Even advanced intelligence cannot escape the structure of space-time itself. The Fermi paradox emerges naturally from these limitations. The galaxy may be full of intelligent life, yet we see no evidence of it because travel and communication across vast distances are fundamentally constrained. Civilizations may develop, flourish, and perish without ever encountering one another. Isolation is not a choice, it is a consequence of the universe's architecture. Even if aliens exist, they are likely confined to their local stellar neighborhood, unable to traverse the distances required to reach other civilizations. Silence in the cosmos is not necessarily evidence of emptiness, but evidence of the scale and rigidity of reality. Even as we examine the immense challenges of interstellar travel, it is essential to recognize what we do not know. Physics has given us remarkable insights into the universe, yet our understanding remains incomplete. We have tested and verified the laws governing matter, energy, space, and time on scales accessible to us, but the universe is far larger, older, and stranger than our experiments can fully capture. We do not yet possess a complete theory of quantum gravity, and we cannot fully reconcile the physics of the very small with the physics of the very large. There may be phenomena or mechanisms that could change the landscape of interstellar travel in ways we cannot currently imagine. But there is an important distinction between what we do not know and what is possible. Unknown does not mean unlimited. The universe has rules, and those rules define the bounds of what is achievable. Even if unknown physics exists, it must still be consistent with everything we have observed so far. Nature does not operate by whims or desires, it operates by laws. These laws are subtle, complex, and sometimes counterintuitive, yet they are unwavering. We can imagine loopholes in the fabric of space-time, shortcuts across the galaxy, or technologies beyond our comprehension. Mathematics allows us to write equations that describe these possibilities. But nature does not guarantee that mathematical constructs correspond to physical realities. The universe is not an empty canvas on which intelligence may paint freely. Intelligence must work within constraints, no matter how creative or advanced it becomes. Our struggle to grasp the scale of interstellar travel is also a reflection of the limitations of human intuition. Evolutionarily, our minds developed to navigate small, local environments. Throwing a rock, crossing a river, walking across a field, these are the kinds of problems our brains evolved to solve. We are not naturally equipped to conceptualize distances measured in light years or the energies required to accelerate a spacecraft to a fraction of light speed. When we hear that the nearest star is 24 light years away, we translate it into a convenient notion of distance rather than appreciating the true, staggering scale. Interstellar distances are not just bigger versions of familiar spaces, they are a fundamentally different category of challenge. They operate in a regime where time, energy, and matter behave in ways that defy ordinary human experience. This recognition brings a certain humility. Understanding the universe requires not only intellect, but the patience to confront scales, forces, and durations that surpass our everyday lives. Even civilizations more advanced than ours would likely face the same constraints. They may develop remarkable technologies, yet the combination of distance, time, energy, and hazards could render interstellar journeys effectively impossible. The galaxy may be teeming with intelligent life, yet isolation remains the default state. Even if contact is theoretically possible, it is practically improbable. Civilizations are separated not by choice, but by the immutable architecture of reality. Yet acknowledging these limits does not diminish wonder, it enhances it. The universe is vast, intricate, and precise. Its boundaries define the stage upon which life and intelligence emerge. We are not imprisoned by these constraints. We are participants within them, navigating a cosmos that challenges our assumptions and expands our understanding. The limits themselves, far from discouraging curiosity, illuminate the subtlety, elegance, and depth of the universe. The absence of easy shortcuts, the impossibility of bending the laws, and the relentless vastness of space all serve to deepen our appreciation of the cosmos. Constraints are not obstacles to curiosity. They are the framework within which wonder flourishes.